All right, we're recording. And so this very last part about chapter 17 is going to be talking about a little less, actually a lot less, on acid-base chemistry and more on chemistry that dictates why certain solutions, you have saturated versus non-saturated solutions, and what's going on the molecular level. So why don't we start taking just an example of calcium fluoride. So let me just open up my iPad and we'll get started. All right. So what we're looking at is the compound calcium fluoride. And I realize on these slides again, I put in the wrong arrows. This should be unidirectional, right? So when a solid is added to water, majority of the time, as long as it's not saturated, right, the calcium will dissociate from the fluoride and then it'll be surrounded by water. And that's what we're seeing here in this picture over here, right? You start as a solid and then water goes in and solvates individual ions and it pulls those into solution. When we start to approach, let me just erase everything. When we start to approach that point of saturation, that's when equilibrium sets up. So it's saying that calcium and fluoride at a certain point, there's so much in solution of Ca2 plus and F minus that actually they start to collide and they'll go backwards and reform the solid calcium fluoride. So like any other reaction we've dealt with, we can write a K expression for this. So again, right, for K, it's going to be products raised to some power over reactants raised to another power. When I look at my balanced chemical equation, for all solids that are dissolving, you're always going to have a solid in the reactants. So when we write out the K expression, there will be no denominator. It is only the products. And what we call this, specifically for solids dissolving into a solvent, is going to be KSP, or solubility product. That's what the SP stands for. And all that's going to be equal to is my products. So I have a calcium 2 plus, I have a fluoride minus, but I need to look at the coefficients in front of these products. I have a 1 in front of the calcium. It's implied there's a 1, but I have a 2 in front of the fluoride. And so when I write out the K expression for this particular compound, calcium fluoride, going into water, we're going to write it as KSP, or the equilibrium constant, equals calcium 2 plus times the concentration of fluoride minus squared. So that shouldn't be anything new. It's just being more specific about talking about a particular chemical process. So, oops, you guys get, oh, there we go. It's gone. All right, so let's read through this slide and start to pull things apart. So I've done the math out already to try to make things a little bit easier, especially when it's a problem where I don't think we need to pull it apart as deeply as some others. So it says, if a concentration of calcium 2 plus aqueous and F minus aqueous in a saturated solution of calcium fluoride, it's known as KSP, right? Oh, sorry, it's R known. Sorry, my bad. R known. KSP can be calculated from that information. We already have our balanced chemical reaction. We know calcium, it's given to us. It's just telling us the concentration. You would not know this off the top of your head. I would have to give this to you. It's saying the concentration of calcium is that number. The calcium of fluoride, the concentration of fluoride is this number, right? When we plug that into KSP, we've already written out the expression. So now it becomes the concentration of calcium times the concentration of fluoride. And fluoride, because of the K expression, is squared. Doing all that math out, we can find KSP. So I don't know if I skirted around this, and I didn't mean to. KSP is technically for a saturated solution. So it's telling you basically once that saturation concentration has been met, and then you calculate how much calcium and how much fluoride are floating around in that solution that's saturated, those amounts are going to give you KSP. So it's the maximum amount of solubility. That's what KSP is, maximum amount of solubility. So I know that, as I realized, because I kind of, it was a circuitous way to describe that. I just want to make sure we're on the same page, what I was just saying. Does anyone need a clarification, or are we ready to go on? All right, I'll take that as a good sign. So why don't we move on? So if we were asked, so it's a different compound now, but asked to calculate the molar solubility of now magnesium fluoride, and again at 25 degrees Celsius, most of the time, right, I already mentioned this goes all the way back to, I think, chapter 15, I need to specify temperature to be technically correct, right? You might not use it, and most of the time you do not use it in the equation. We can treat this similar to an ice table. Again, right, anytime we deal with KSP, it's everything below saturated. KSP represents saturated. So that means everything goes to products. So again, I gotta fix these slides. I'm sorry about that, right? Everything's going to products. So it doesn't matter how much I start with, because I'm not dealing with a regular ice table. But what we've seen with like ice tables is keeping those coefficients intact. So we'll make one X amount of magnesium, depends on how much magnesium fluoride I have, but an X amount will come out. And because it's always in a 1:2 molar ratio, 2 times as much of fluoride will also be in solution. I was given the KSP. So if I know my KSP expression, which KSP equals basically products over reactants, reactants are going to be always solids when we deal with KSP. So what I can look at is saying, well, when things are all said and done, I'll have an X amount of Mg2 plus and 2 times that, or 2x fluoride. I plug that into the expression. What it looks like then is X times 2x squared. So that becomes 4x cubed, because that 2 is going to both the 2 and the x, and so the square. So it becomes 4x squared times x, which becomes 4x cubed, which we see down here. That's high school algebra, right? The nice thing with this, that's a pretty easy problem to solve for. You divide both sides by 4, and then you take the cubic root. And so make sure you're comfortable using your calculators to take cubic roots. Just like square roots, just make sure you can do cubic roots. When you take the cubic root of 7.4 times 10 to the negative 11th divided by 4, cubic root, well, that's going to give me x. What does x equal? The concentration of magnesium, right? And so what I'm looking at, the concentration of magnesium at its maximum solubility for magnesium fluoride at 25 degrees Celsius is 2.6 times 10 to the negative 4th molar. This term here, molar solubility, another way you can think about this is just max solubility. It's how much magnesium could I get into solution, or just X in general, right? It seems pretty arbitrary, kind of is, right? If we were looking for the maximum concentration of fluoride, well, for magnesium fluoride, because there's 2 times as much fluoride that is formed, the max solubility would just be 2x. So the way scientists get around that problem is just to get to the lowest common denominator of 1. So it's just saying x is equal to the maximum solubility, and that maximum solubility is 2.6 times 10 to the negative 4th. And that refers to anything that has a coefficient of 1. I hope I didn't lose anyone on that explanation. Are we good? Do you want a better explanation? Can we go deeper? What is everyone feeling on this? All right. I'll keep moving forward. Don't have too much left, right? So what I'm going to do now, so this is, I think goes back to last Friday, maybe something like that, when I recorded some lectures about common ion effect and also buffers. So we saw buffers come up again during titrations in our last couple of videos. Now common ion effect is making its reappearance now, right? Common ion effect, to remind people, just means that when I have two different types of ionic compounds mixed in the same solvent, in this case water, right? Magnesium fluoride and sodium fluoride share a common ion of fluoride. So we're asking the question, so we already calculated the maximum solubility of magnesium fluoride in the last slide, right? On the order of magnitude of 10 to the negative 11th, right? Sorry, was it 10 to, let me actually go back. I don't want to misquote myself. Sorry, 10 to the negative 4th, big difference, right? What happens if I try to dissolve magnesium fluoride into a solution that already contains fluoride through sodium fluoride? How would that affect the solubility of that solid magnesium fluoride? Stop, you think, ask yourself the question, what would this look like? Again, right, we're talking about maximum solubility. So again, sorry, unidirectional arrow, right? Magnesium fluoride dissociates in a 1 to 2 molar ratio because I have one magnesium, 2 fluoride, 1 to 2. How much magnesium dissolve? I don't know. That's why it's X. How much fluoride dissolve? I don't know, but it's 2 times as much as X because it's MgF2. However, right, I've already have a solution of 0.1 molar sodium fluoride. There is a 1 to 1 molar ratio between sodium and fluoride, so it means when it dissociates, fluoride's concentration will be 0.1. So we need to stop and think, evaluate what's actually physically happening, and don't go off of rote memorization, right? I already have a solution that has 0.10 molar fluoride. I'm dissolving more magnesium fluoride into that solution. Excuse me. What happens? Well, then we need to take that into account. It becomes a little bit more difficult with math. Again, I have my KSP. This is from the last slide. Same compound, same maximum solubility, 7.4 times 10 to the negative 11th. I have my KSP expression, magnesium times fluoride squared. And then I go through and I do my math. Magnesium's concentration is going to be X. Fluoride's concentration is going to be 2X. I already have the 0.10 molar, and according to the expression, it needs to be squared. This gets complicated and out of hand really quick, right? We need to be comfortable with our assumptions, right? We're going to have to assume that X is really small compared to 0.1, right? If we make that assumption, that's what I have down here. If I wrote things out the long way, that's what we're doing. You're dealing with cubic roots and you're getting to the limits of easy math, right? You're going to have to go through much higher math to do anything beyond cubic roots. There is no such thing as a quaternary root or quadratic equation for fourth order polynomials. Doesn't exist. Well, it does, but it's super hard. Anything beyond that doesn't not exist, right? So it becomes hard to do the math. We need to rely on these assumptions. So if 2x is very small, specifically if 2x is much, much smaller than 0.10, well, then effectively, this little thing here in the parentheses, so if 2x is super tiny and you're adding it to 0.1, well, it's effectively 0.1. And what did I do? All I did was make my math a heck of a lot easier. So you square 0.1, you multiply it by x, then you solve for x. Pretty easy. X is going to be the maximum solubility or the molar solubility of Mg2+. So we're comparing to the last slide. There's my KSP divided by everything that wasn't X. Do the math out. 7.4, don't really care about that number, but the order of magnitude is 10 to the negative ninth. Remember, we're comparing this to when MgF2 was dissolved in pure water. Pure water, order of magnitude 10 to the negative fourth. With sodium fluoride present, the solubility has decreased at this point, let's see, 1, 2, 3, 4, 5, 10,000-fold less when the sodium fluoride is present. That is the common ions effect. It's driving the reaction in reverse. And that's why I do have, and it's not a mistake, that's why I do have those equilibrium arrows. When we talk about KSP, yeah, we talk about unidirectional. When things get more complicated, yeah, reactions can go in reverse, and we're seeing that solubility has gone down for magnesium fluoride. That's telling me if I exceed this concentration in terms of the magnesium 2+ ion, anything beyond 7.4 times 10 to the negative ninth molar for Mg2+, it's going to precipitate. It's going to come back out of solution because it's saying you hit your maximum solubility, nothing's going to go forward. It's going to stay as a solid. That's the power of the common ion effect. I said a lot in that one slide. Does anyone want me to clarify, talk about, or touch on anything else? All right. So let's keep moving on. We don't have too much more to do, right? So this is the same. I should probably shown this in the last slide, right? But the molar solubility we calculated 2 slides ago, don't really care about the number. 10 to the negative fourth is my order of magnitude. When I added some sodium fluoride, you can see it precipitously drops to 10 to the negative ninth. So literally 5 orders of magnitude. So 10,000-fold, right? Why does this happen? Well, it literally comes down to Le Chatelier's principle. When we're thinking again of things that are in equilibrium, we have our reactants and products. Well, basically what's happening when I put that sodium fluoride in there, I'm already weighting the scales towards the product, right? So if I add a little bit more of that magnesium fluoride, the only way the reaction is going to go back to equilibrium is to make reactants, making it less soluble, right? So Le Chatelier's principle is describing why, when you have the common ion effect happening, magnesium fluoride is less soluble than sodium when sodium fluoride is present, or any kind of fluoride compound is present. And what we're seeing here, exactly what we hear, right? Pure water. This is exactly what we saw. I'll go through this slide pretty quick. I know it's kind of overkill now, right? Pure water. As you start to put in more and more fluoride ions, we see the solubility of that compound, magnesium fluoride, plummets. And that's what you'd expect. There's a lot more F2 or F minus floating around. That means more things are going to go back to form solid. That means there's less solubility. This one's a little bit weird. I wanted to include it because we're talking about acid-base chemistry, but the same thing happens when you're dealing with other compounds. It doesn't have to be fluoride, right? I have calcium carbonate reacting with hydronium to form calcium carbonate and water, or bicarbonate and water. This graph, I know I should change it. I haven't changed it in like a year. I'm sorry. Little confusing, but remember, as pH goes down, the concentration of H3O plus goes up, right? So as the pH goes down, the amount of hydronium goes up, which then drives the reaction forward, right? And that's why you're seeing an increased solubility. So there are ways you can also increase solubilities of solids, especially if they react with hydronium. It's a specific example. Maybe I shouldn't have included it. Now I feel like it's probably a little bit more complicated. I don't mean to confuse people, but right, we're thinking about Le Chatelier's principle in conjunction with this new idea of KSP. How does affecting equilibrium push something either into solution, like what we're seeing on this slide, or out of solution, like we were seeing on the last slide. Hopefully this will go a little bit quicker. We've seen this before. There's nothing new on this slide. We have KSP. Consider it K. You can write Q. I put subscript T because it means some time that's not at equilibrium. You could also call it sub I, or whatever you want to call it. It's basically, Q is not at equilibrium. Don't worry about those sub T's too much. The only difference, and this kills me, I hate it, but when you're dealing with solids going into solution, Q changes its name to IP, to ion product. There is no difference in the rules whatsoever. Same idea. Q and K are compared just like we did with chapter 15, except now because we're dealing with solids, we call it IP instead of Q. Only difference. Everything else holds the same. The only slight difference, I would say, instead of going in reverse versus forward, these things still mean the same thing, right? When you go back towards product, the difference, instead of saying we go back towards the product, is it will say there's precipitation. Why? Because when we look at something like calcium fluoride, it's a solid. It's not going to be soluble in water, so it precipitates, right? IP equals KSP, equilibrium is achieved, means it's saturated. If IP is less than KSP, precipitation will not occur. That basically means we're going in the forward direction, and we're going to keep going in this forward direction until we hit equilibrium. That's all that means. So no rule, literally no rules have changed. And that's going to be the end of our slides. And we're done. This is literally the end of the course. So if we have any questions, I'm happy to take them. I know we finished about 15 minutes early, but it's Friday. If you want to head out 15 minutes early, be my guest. If not, I'm going to stick around for a couple of questions. So like I said, if you want, head out. If not, I'm around. I'll stop the recording.
Do you know how to do the math on that's like on Mastering Chem?